Good morning. Well, it's morning when I'm making this. I'm not sure what time of day it is when you'll be watching it. This is Foundations 30, and um, when we left off this course, we were towards the end of Chapter 5. I'm going to leave Chapter 5 as it is. I'm going to skip ahead to Chapter 6. That's where we're going to start our next set of lessons, and that's going to start with Section 6.1, the graphs of polynomial functions. We're not going to have a test on Chapter 5. If we ever do get back to this year and have some sort of final, we'll review all of that material. But at this point, I'm not going to worry about having a test. At the beginning of the year, when we went through the course outline, I talked about this course being divided into groups of chapters. We just finished chapters 3, 4, and 5, which were a group by themselves. All three were related. The next three are also going to be related. We have chapters 6, 7, and 8 all deal with functions of some sort. And in this chapter specifically, we are going to deal with something called polynomial functions. So let's get rid of my ugly face. Okay, I'm good looking. I have to admit that. And let's work through our notes for section 6.1, polynomial functions. So our goal for this next half hour or so is to explore something called the end behaviors for the graphs of polynomial functions. So in order to get to this point, we have to recall some definitions that we learned back in Foundations 10. In Foundations 10, we talked about a relation. And a relation is an association between the elements of one set and the elements of another set. So in the world of algebra, we're usually talking about the relationship between a set of x values and the set of y values, which brings us to our next definition, the domain. The domain is the set of all the first coordinates, or the x values from our relationship. And the range is the set of all the second coordinates, or y values, from our relationship. Now, when we did Foundations 10, we stressed the word relation. A relation shows the association between any two sets of objects. Then we had a very special type of relation, and that was a function. So the key thing to remember here is a function is a relation. A function is any relation in which each element of the domain has a unique element in the range. So that means for each x value can go to only one y value in the range. And we say if it does that, it passes the vertical line test. So if you have printed off these notes, there is some space at the bottom of this page. So I'm just going to go down and draw a few diagrams. You might want to add these diagrams yourself. So let's see if I can do this here. I'm still learning how to use all of these new toys that I've got for these lessons. So if I draw a coordinate axis and label it x and y, if I drew a parabola, what we are saying is that this value of x would go to only that value of y, or that this value of x would only go to that value of y. So basically, it's passing the vertical line test. If I put a vertical line at any point on this graph, it'll cut the graph at one and only one point, no matter how it works. Let's draw another graph. Let's take our parabola and let's tip it over this way. Now, if I pick a value of x, let's say my value of x is right there. If I draw a vertical line through here, we are cutting this graph in two spots. So we say this fails the vertical line test. This one value of x goes to two different values of y, one above, one below. So this is an example. This is a relationship. It shows the association between two different sets of objects, but it does not qualify as a function. Now I have a feeling if I move this back up, oh, it did stay down. How about that? That's awesome. Like I said, I'm learning how to play with these new toys. So hopefully, as the days go on, I get quite quick at being able to switch back and forth from these pointers. All right, enough rambling. This chapter talks about polynomial functions. And a polynomial function, in order to be a polynomial function, three conditions have to be met. First of all, we have to have two variables. And for this course, 90% of it is going to be x and y. We might change. For some reason, it could be c and d. It could be k and l. I don't know why we would. Well, actually, I can think of several other reasons we would use different variables. But for now, we're only going to worry about x and y. It will only have the mathematical operations of multiplication and addition. Now, whenever I talk about multiplication, multiplication also implies division. Division undoes multiplying. They're one and the same. So the same thing for addition. Addition is connected to subtraction. One undoes the other. In fact, back in grade 8, when we talked about dividing fractions, you were always told to multiply by the reciprocal. Every division question can be turned into a multiplication question. In grade 8, when you first started algebra and you were dealing with subtracting expressions, you were always told to add the opposite. Every subtraction question can be turned into addition. All right, moving on. It must also have real number coefficients. That means the numbers in front of our x or y value could be any real number in the universe, and our exponents must be whole numbers. Now, whole numbers means they have to be positive, and there can be no fractions. Now, what does that mean? Well, if our exponent is positive, that means there is no variable in the denominator. If I go back to my pen here, if I write this expression, that's 1 over x. Well, if I take this x and move it to the numerator, I can do that by making the exponent negative. And we learned that back in Foundations 10 when we dealt with exponents. If we move a term across this fraction line, we switch the sign of the exponent. Now, whole number exponents means they have to be positive. So in this case, this would fail. And if they can't be fractions, well, that deals with this type of expression. If we have root x, that's the same thing as x to the power 1/2. So when we are dealing with polynomial expressions, there will be no radical symbols, and the variable can never be in the denominator. That's what it means to be a polynomial function. In chapter 6, we are going to look specifically at three types of polynomial functions. And the first type is something we studied in Foundations 10. It's called a linear function. And a linear function is a polynomial whose degree is 1. That is, the greatest exponent is 1. Now, if I look at this example, I have an equation here, y equals 2x minus 3. It's not written in, but if I looked at the x value, the exponent is 1. And if I look at the y value, the exponent is 1. It's not written in, but we assume it's to the power 1. Now let's look at the graphs of these. Here are two examples. I have taken the opportunity to take these examples and put them onto Desmos. So there's our first graph. Obviously, linear, the root word is line. And when we graph a linear function, the result is a line. We don't need to say a straight line. All lines are straight by definition. Now, if you have printed off the notes or if you are following along, you will notice that underneath this graph, it's asking us to state the domain and the range. Now, when I find the domain and range, I always ask myself two questions. And to do this, I'm going to turn my spotlight back on. And when I'm talking about the domain, I'm asking this question. If I had an infinitely large screen, would this graph go backwards forever? And would this graph go forwards forever? And if we look at this line, I have an arrow on that axis, an arrow on my y-axis, indicating that we can't possibly draw an infinite graph, but those arrows indicate it does go on. And if I look at this line, it does go in this backwards direction. It does go in that forwards direction. So we say the domain is the set of all real numbers. This graph would extend forever backwards, forever forwards. Same thing, when we talk about the range, I ask myself two questions. Does the graph go down forever? Does the graph go up forever? And in this case, the line is moving on an angle. So yeah, it would continue downwards forever in that direction, and it would continue upwards forever in that direction. So the range is the set of all y values that are elements of the real numbers. If I look at the picture on the right, it's a line that looks like this. This line is moving in a downward direction. Every time I change screens, my picture shows back up. All right. So if we were going to find the domain and range, we would ask ourselves the same two questions. Does this graph go back forever? Does this graph go forwards forever? And again, that answer is yes. When we're talking about the range, we ask ourselves two questions. Does it go down forever? Does it go up forever? And again, that question is also yes. So if we go back to our notes, oh, sorry, wrong window. That's going to be annoying. I'll have to see if I can find a way of turning that off. There's our domain and range. For every line in the universe, the domain will always be all real numbers, and the range will always be all real numbers. Now let's talk about the quadratic function. Quadratic function is any function of degree 2. That is, the greatest power is 2. So if I look at this particular expression, x squared minus 5x plus 4, the highest power is the 2, meaning this is a quadratic expression. Now, in Foundations 20, Chapter 7, you will have learned that when you graph every parabola in the universe, the shape is something called a parabola. When you graph a quadratic, I'm not sure I said that properly, when you graph a quadratic, the shape is always a parabola. And our parabolas will have one of two forms. The one on the left here opens up. The one on the right opens down. So again, I've taken the opportunity to put these into Desmos. And if I look at this first graph, if I wanted to talk about the domain, I would ask myself, does this graph go backwards forever? Does this graph go forwards forever? And the answer would be yes. This parabola is getting wider and wider as it moves upwards. So since it's getting wider and wider, that means it is moving backwards forever. It is moving forwards forever. So our domain would be all real numbers. When we deal with the range, we have to ask ourselves two questions. Does it go down forever? Does it go up forever? And in this case, the graph doesn't go down forever. The lowest value it gets to is right here at this vertex, which has coordinates 0, minus 2. However, the graph does go upwards forever. Now, because all of the y values are moving in an upward direction, when we talk about this vertex, one of the words we use to describe this vertex is minimum. It is the lowest point on our parabola. So all of our y values are above this. Now again, if I highlight the coordinates for this particular vertex, the vertex was at 0, -2. All of our y values are above the -2. So when I state the range, my range is going to be all y values greater than or equal to the -2. All the y values are above that. Now let's focus on the second parabola. Second parabola is concave down. Now, there's my vertex at 0, +2. If I talk about the domain, first of all, if I'm going to talk about the domain, I'm going to ask myself two questions. Does it go back forever? Does it go forwards forever? And the answer would be yes. This parabola is constantly getting wider and wider as it moves down. And if it's getting wider and wider, that means it goes back forever. It moves forward forever. So the domain would be all real numbers. When I'm talking about the range, I ask myself two questions. Does it go down forever? Does it go up forever? In this case, it does go down forever, but it doesn't go up forever. Eventually, it gets to this point, the vertex, which is at 0, 2, and then it turns around and moves back down again. So all of our y values are below this vertex. So if I look at my range for this particular graph, we say all our y values are less than or equal to 2. All our y values are below that particular vertex. There is a third type of function we're going to look at in this chapter, and this is one we have not seen before. And so I'm going to introduce it briefly today, and it's called a cubic function. And if we have a cubic function, that means it's a polynomial function whose degree is 3. So if I look at this particular expression, the highest power is 3. And when you graph a cubic polynomial, you usually get a graph that looks something like this. It moves upwards, moves downwards, and then it turns around and goes upwards like that again. And then this one goes down, up, and down like so. Let's talk about our domain and range. So I've taken the opportunity to graph these ahead of time. Now, oh, that's not quite what I wanted to do. If we look at this graph, and I wanted to talk about the domain, I would ask myself two questions. Does it go back forever? And does it go forwards forever? And in this case, the answer would be yes. This graph is constantly spreading out. If we look at it, it's tough to see on a smaller screen, but this would continue moving back to the left as it moved in that downward motion. And this would continue moving forever to the right as it moved in that upward motion. So our domain is all real numbers. And I've already answered the range question. Does it go down forever? Yeah, I said that this continues down forever. And does it go up forever? Yeah, that one continues up forever. So our range is also all real numbers. And if I look at the next graph, the next graph looks like this. And if we focus on the two questions, does it go back forever? Does it go forward forever? The answer in both cases is yes. This is moving, as this continues to move upwards, it is moving back to the left. And this, as it continues to move forwards, as it continues to move in this downward direction, is always moving to the right. So our domain is all real numbers. And if we look at it in terms of our range is also all real numbers. It goes forever upwards and forever downwards. So for this cubic graph, our domain and range are all real numbers. Now, I want to talk about two more terms. I want to talk about end behavior and turning point. And end behavior is the description of the shape of the graph from left to right on the coordinate plane. Now, we can make that a little simpler. When we talk about end behaviors, it's basically asking what quadrant does the graph start in? What quadrant does the graph end in? And when we talk about that, it's just like reading a book. When we talk about starting and ending, it's as we move from left to right. Now let's do a review of a coordinate axis. I've got some room at the bottom of this page here. I am going to turn my pen on and let's make it blue. When we have our coordinate axis with arrows indicating it goes on forever in all directions, and we should, every time you draw an axis, you should label the horizontal axis X, the vertical axis Y. We divided our coordinate axis into 4 sections, which we refer to as quadrants, and the quadrants are numbered. The upper right quadrant is referred to as quadrant 1. And I'm assuming we start there because everything is positive. Our x value is positive, we've moved to the right. Our y values are positive, we've moved in the upward direction. And then we move counterclockwise. This is quadrant 2. Here is quadrant 3. And here is quadrant 4. And when we label our quadrants, we always use capital Roman numerals. I have no idea why that is, but that's the way it is. It's just one of those things that's done. So if I'm asking you to label quadrants, you must use capital Roman numerals. If you don't, you've technically done it wrong, and I will take off a half mark for that. Quadrants must be labeled with capital Roman numerals. All right, turning points. Turning point is any point on the graph of a function where it changes from increasing to decreasing or from decreasing to increasing. Now let's go back to our graphs. Let's go back to our lines. Our lines were at the top here. Sorry, I went too far. If we look at our lines, this line is always increasing. As I move from left to right, it's always moving in the upward direction. This graph on the right is always decreasing. As I move from left to right, it's moving in a downward direction. So this never changes. So we say that lines have 0 turning points. Let's go down to our parabolas. If we look at this graph, it starts as I move from left to right, it's decreasing. We get to our vertex and then it turns around and starts to increase. So we refer to this as a turning point. So this parabola has 1 turning point. If I look at this graph, as I move from left to right, it starts in an upward or increasing direction, gets to our vertex, turns around and changes to decreasing. So again, 1 turning point. If I look at our cubic functions that we had, on the left here, it started in an upward or increasing direction, changed to decreasing, and then got to this point and turned around and went up again. So we say this graph has 2 turning points. Similarly, if I look at the graph on the right here, it was decreasing, it was moving downwards, got to that, I hate to use the word vertex because that word is saved specifically for parabolas, turns around and moves upward, gets to that maximum value, and then turns around. So we say we have 2 turning points, 1 there and 1 there. Now, let's talk about our end behaviors. I'm going to move back up to our lines again, and I'm actually going to go to our Desmos graphs. If I look at this graph, here's my origin. As I move from left to right, the first time I see the graph is right here, which is in quadrant 3. So we say that this graph starts in quadrant 3. And as I continue to move to the right, the last time I see the graph up here is in quadrant 1. So when we talk about the end behaviors for this line, we say it starts in 3, ends in 1. Let's go to the second line. As I move from left to right, the first time I see the graph is in the upper left-hand corner, which is quadrant 2. And as I continue moving to the right, the last time I see it is in the bottom right-hand corner, which is quadrant 4. So we say that this line starts in 2, ends in 4. If I go to this parabola, as I move from left to right, the first time I see it is in quadrant 2. And the last time I see it is over here, which is in quadrant 1. If I look at this parabola, as I move from left to right, the first time I see it is in the lower left corner, which is quadrant 3. And the last time I see it is in the lower right corner, which is in quadrant 4. And if I go to my cubic graph, this one started down here in quadrant 3. And as I move to the right, the last time I see it is over here, which is in quadrant 1. And moving to the last cubic, this particular one started over here in quadrant 2. And the last time we see it is down here in quadrant 4. So that's what we're talking about when we say the end behaviors of a graph. Now, we've only talked about linear, quadratic, and cubic functions. That is hardly enough to establish a pattern, but there is a pattern. Now, I'm going to flip back and forth between these Desmos graphs. So hopefully this does not get too confusing. Here was the first line we did. It started in quadrant 3, ended in quadrant 1. This was the first cubic we did. It started in quadrant 3, ended in quadrant 1. The second line we did, the decreasing one, started in quadrant 2, ended in quadrant 4, and the last cubic we did started in quadrant 2, ended in quadrant 4. That is the same. So the question is, what's the connection? And the connection has to go back to the degree. Linear functions are of degree 1. Cubic functions are of degree 3. Those are both odd numbers. Odd numbers. And if we look at the parabolas, parabolas are of degree 2, which is an even number. So if you look at the summary chart at the end of our notes, let me get back to my pointer here. And we're just about done. If you're getting bored, we're just about done here. Here we are in the summary chart. When we talk about polynomial functions, we always look at the degree and we classify it either as an odd degree or an even degree. Now, if we go back and look at lines, what determined whether our line was moving in an upward direction or a downward direction was our slope. So when we're talking about lines, we talked about y equals mx plus b. I'm just going to write that over here on the side. Y equals mx plus b. And this m, the coefficient in front of our x, determined whether this line was going to be moving in an upward direction, moving from quadrant 3 to quadrant 1, or a downward direction, moving from quadrant 2 to quadrant 4. And we refer to this m as the leading coefficient. It's the number in front. And if that number is positive, it's going to start in 3, end in quadrant 1. And if that number is negative, it's going to start in quadrant 2 and end in quadrant 4. And that will be true for every odd function in the universe. Now, let's talk about our even functions. That's the parabolas. If I write the equation of any parabola was y equals ax squared plus bx plus c. That's what we learned back in Foundations 20. And so if I look at this leading coefficient, the number at the very front, if this was positive, that meant our parabola was going to open up. And if this number in front was negative, that meant our parabola was going to open down. If this number was positive, our graph parabola opened up. If that leading coefficient was negative, this graph opened down. And that's going to be the case every single time. Every time we are dealing with a polynomial function, we simply have to ask ourselves, is this function odd or is this function even? Then we are going to look at our leading coefficient. If the leading coefficient is positive, it's always going to go from quadrant 3 to 1. If our leading coefficient is negative, it always goes from quadrant 2 to quadrant 4. I hope this made sense. This is very tough for me to do. I can't see your faces. And if I can't see your faces, if I can't see your eyes, I have a hard time knowing if I'm getting through to you. So as you watch this video, if you have questions, if I'm explaining something that you're just not getting, make sure you send me an email at kfriesen, how does that work? Sorry, kfriesen55@chinooksd.ca. It's on the course outline you got on the first day. You can also contact me through the Google Classroom. So this video, I'm going to embed it into the 6.1 notes. I'll make an announcement on the Google Classroom. Hopefully you find it. I encourage you, work through this material as I post it. You're going to get a phone call from your homeroom teacher over the next couple days, and they're going to ask you what you want to do in terms of your marks. And then when we get back after Easter, we'll discuss that in more detail. So anyway, thank you for watching this video. Hopefully you're not bored to tears. Stay smart out there. Please keep isolating and stuff. That's the only way we're going to get through this. Thank you for watching.